Look closely at a single ant crossing the dirt. She isn't taking orders. She hasn't memorized a master plan. She is operating completely on her own. Even the queen isn't in charge. Her title is a bit misleading. She doesn't command the colony. She is a biological factory laying thousands of eggs a day, acting as the permanent hard drive that holds the family's genetic code. Yet, without a manager or an architect, these insects build subterranean cities plunging 25 feet deep. They engineer precise climate-controlled nurseries and maintain complex underground fungal farms. To understand how they do this, we have to shift our perspective. An individual ant is not a whole animal. It is a single cell operating inside a much larger body. The entire colony functions as a massive distributed computing system running on a biological tech stack. Let's reverse engineer its layers, starting with the individual nodes. As a piece of hardware, the worker ant is heavily over-engineered. She is capable of carrying objects 50 times her own weight. This diagram illustrates the square-cube law. As an object shrinks, its volume decreases faster than its cross-sectional area. Because she is so small, her muscles are incredibly thick compared to the low weight of her own body, giving her extreme strength relative to her size. Attached to this muscular chassis are her primary peripheral devices, the antennas. By moving them, she processes smell in 3 dimensions, allowing her to pinpoint the exact direction of a target. These sensors also allow for a process called antenation. When 2 workers bump into each other, they rapidly tap their antennas to exchange peer-to-peer data, verifying their colony signature smell or sharing the coordinates of a food source. The worker ant is a highly optimized titanium-tough node. She is perfectly equipped to process environmental input and move heavy amounts of physical matter. A single node is practically useless without a network. Across the forest floor, these workers are constantly communicating through an invisible chemical web. As a scout searches for food, she leaves trace amounts of scent molecules called pheromones on the ground. These act like chemical SMS messages, guiding her sisters toward the resources she finds. This routing graph breaks down the math behind ant colony optimization. The probability of an ant choosing a specific path depends on the intensity of the pheromones left behind. If a path is shorter, ants travel it more often, depositing more scent. That higher intensity attracts more ants, creating a self-reinforcing loop that calculates the optimal route. Networking continues inside the ant's own anatomy. Every worker possesses a secondary organ called the social stomach, used strictly for storing liquid food for the rest of the colony. When a successful forager returns home, she unloads this payload to her sisters through trophallaxis, a direct mouth-to-mouth liquid exchange. This liquid contains complex hormones and system status updates. As the fluids are passed from worker to worker, the chemical data ripples through the nest, signaling whether the factory is running smoothly or if danger is near. Through a combination of external trail pheromones and internal shared nutrients, millions of decentralized insects maintain a biological high-speed sync that keeps the entire system aligned. The true power of this network reveals itself when the environment fights back. A deep ravine or a sudden flood presents a fatal obstacle for a single insect. They overcome this through emergent behavior. The colony relies on simple embedded instructions, soft rules like, if you encounter a gap, stretch your body across it. When thousands of army ants execute that rule simultaneously, their limbs lock together over empty space, constructing a living bridge out of their own bodies. Fire ants use a similar program during severe floods. By linking jaws to legs, they combine the waxy coating on their exoskeletons with the water's surface tension to form a massive, waterproof raft. These macroscopic survival strategies require no central planning. They are the direct, mathematical result of millions of tiny, supportive instructions executing perfectly in parallel. Scaling this system up explains why ants dominate the planet. Today, this leaderless architecture accounts for roughly 15% of Earth's total terrestrial animal weight. They act as the Earth's ecological guardians. By endlessly aerating the soil and recycling decaying matter into nutrients, they maintain the baseline stability required to keep the global ecosystem from crashing. By 2026, human engineers have recognized the extreme efficiency of this model. Instead of deploying single, expensive, monolithic machines, we are now building swarms consisting of thousands of simple ant bots. Using the exact same pheromone algorithms and soft rules, these biomimetic swarms can autonomously route high-speed internet networks, clean up hazardous material spills, and construct modular habitats on the moon. The ant colony serves as a functional model for high-stakes coordination. It demonstrates how simple, supportive microbehaviors allow a decentralized group to solve physical challenges that no single leader could ever calculate.